Right, this is electricity part 2. I'm going to go through charge, current, potential difference, and resistance, so what they are. Right, so the first thing is that current is the rate of flow of charge. So charge is a property of matter. I've written a little crib sheet down here just to help out because the symbols are a bit confusing. So charge is like a property of matter. Electrons have a negative charge, protons have a positive charge. Not much to say about that, right? That's just a thing that matter has. Charge. The symbol for charge is Q, so instead of writing the word charge, we write the letter Q, and charge is measured in coulombs. The symbol for coulombs is capital C. Now, current is the rate of flow of charge, so it's how much charge passes a point every second. The symbol for current is I, because I think it's French, intensity of current, and it's measured in amps, which is A. Potential difference is the energy that current is carrying. So the energy that current is carrying, we tend to measure it as a kind of like what the change in potential difference is across 2 points in a circuit. And that is measured in the symbol for potential difference is V. Used to be voltage, and you can use voltage, but they talk about potential difference in the exam. But you can say, oh, the voltage is this. And that's measured in volts, which is also V. Resistance R is anything that a resistor, anything that reduces the flow of current. Instead of resistance, we can write the letter R. It's measured in ohms, which is given this symbol here, and then time is measured in seconds. Now, current is the rate of flow of charge. So if I direct you to this equation here, current is the charge divided by the time taken for that charge to flow. A bit like speed is the rate at which your distance increases. So speed is distance divided by time. Current is the rate of flow of charge. More usefully though, we write it like this. And on the equation sheets, it's given as Q is IT, where Q is the charge measured in coulombs, I is the current measured in amps, and T is the time measured in seconds. So Q is IT. That's how we figure out the charge passing a point in a circuit. Now, in order for charge to flow in an electrical circuit, you need two things. You need a closed loop. Charge isn't going to flow if there's a break in the circuit. It has to be a closed circuit, right? A complete circuit. And also a source of potential difference. So like a cell or a battery, or it could even be like for the electromagnetism part of the course, you moving a wire in a magnetic field. Now, I've got a little model of this here. So this, if you'll forgive me for the toy, sellotape represents my circuit, right? Now, it's important to remember that, so just in this circuit here, the electrons are already in the wire. The battery doesn't spew out the electrons. It's really easy to think, oh, the battery fires the electrons out. It doesn't. The electrons already exist inside the circuit. They're the free electrons, part of the metallic bonding in your wire or whatever it is in your component. They're already there. All the battery does is provides energy to move them around. Now, actually, what happens is complicated. They kind of shunt each other along. But you can think of it like this. So if I just hold that there, then I can be a source of potential difference by doing this, right? I'm giving them energy. And look, it's beautiful. They're all moving around the circuit, just as I anticipated. So these little beads are supposed to represent the electrons in the circuit. Now, so they're flowing, right? Each one, if you imagine each one to be like an electron, or say imagine each one to be a coulomb of charge, how many go past this point every second would be the current. Now, I'm going, reasonably slowly. If I increase the potential difference of my cell and I try and go faster, right, they go faster. But I'm putting more energy in, we're getting more current flowing. Does that make sense? So you can model it like this. Now, obviously, if this wasn't a complete circuit, so if I was to break the circuit and just undo this little bracelet, it's not going to work. I don't get a current flowing. Sometimes I can push some electrons around the circuit, but I'm not going to get a current flowing if I try to push them around, try to put a source of potential difference. Now, if, however, I add something into my circuit. I mean, this is a short circuit. There's nothing in here. The current would flow really, really quickly. If I put something in, so say I put my finger here. Now, this is providing a source of resistance. That's getting, even though I'm still kind of going at the same rate I was before, the current is not flowing as quickly. And the beads are all kind of rubbing against my finger. So eventually, my finger get warm. Friction is occurring, right? The beads bashing into my finger. So this cell is providing energy, and then this resistance is making it harder for the current to flow because I'm kind of pushing into them. It's much easier when there's nothing there to get the current flowing. But if I put this here, it's harder to get the current flowing. And also I'm using, my hand will be gaining energy because friction will be causing it to get warm. And if my hand was a light bulb, the current would actually make my hand get so hot it would glow and burn, right? So this is my little diagram of just a simple series circuit, just to explain. I guess the main things are that the electrons are in the circuit at any one point. So they're already in there. These electrons are already in this circuit. The battery provides potential difference, which kind of just gives them some energy, which causes them to move, but they kind of like shunt each other all around. And then if I put more potential difference in, I'm going to get more current because it's going to go around quicker. And if I put a resistor in, that's going to reduce the current because it makes it harder for the electrons to travel. So the current depends on the resistance, so how much whatever there is in the circuit that's slowing it down, and the potential difference of the cell, so how much kind of energy per coulomb you're given. A greater resistance, so if the resistance is greater, that means you're going to get a smaller current for the same potential difference, right? And that's just a kind of a fact. And there are components, but if I was to add an additional resistor in here, overall the resistance of the circuit would increase, which means a smaller current would flow. Now, this can be done in equation form. So potential difference, so this is potential difference measured in volts. This is current measured in amps, in volts. And this is resistance measured in ohms. Now, this explains how they link. If I divide both sides by R, these are cancel, and then I get the current is the potential difference divided by the resistance. So with this, if I examine this equation, if I make the potential difference bigger, I'm making the numerator bigger, and so this fraction is going to be bigger. If I make the resistance bigger, I'm making the denominator bigger, and so this fraction is going to be smaller. So the current is the rate of flow. So the current is potential difference divided by the resistance. And if you increase the potential difference, the current will increase. If you increase the resistance and keep the potential difference the same, the current will decrease. And obviously vice versa. Decreasing the potential difference will decrease the current. Decreasing the resistance, though, will increase the current for the same potential difference. Now, it's something that obeys this law is called ohmic, and you can apply this law to any point in your circuit. If I know the potential difference here and the current there, I can find the resistance. And practically, we can find the resistance of components because we can plug an ammeter. So this is me trying to find the resistance of this resistor here. So I'd plug an ammeter in, which would give me a value for the current. I put the voltmeter in, the voltmeter goes in parallel. It measures the potential difference here. So if this is a 1.5 volt battery, the electrons, the battery or the cell is giving 1.5 joules per coulomb of energy, and then they are losing 1.5 joules per coulomb of energy here. So you can kind of sometimes, although it's not a vector, think of it as like plus 1.5 volts, and here they lose 1.5 volts. But my voltmeter only measures the potential difference. And sometimes it's helpful to trace it around. So my current flows from positive to negative. That's the positive cell. So all the way around here, 1.5 volts, 1.5 volts, because they get given it here, if you like, 1.5, 1.5, 1.5. When they go through this, they lose the 1.5 volts, and so it goes back to zero. And a bit like a waterfall always has to fall to zero, the electrons will always fall to zero before they go back into the cell, right? There's zero potential energy when they arrive there. Electricity is complicated, but thinking of it as electrons already in there being pushed around the circuit, gaining potential energy, potential difference through the cell, and then dropping it off at the components works very well, right? So I could use this circuit, I could measure the potential difference here, and then if I wanted to find the resistance, I would say the resistance is the potential difference across a component divided by the current flowing through it. And that's how resistance is defined. It's not a gradient or anything like that. Resistance is for what is the current for that potential difference, and it's the ratio of potential difference to current at a particular moment in time. Because for most components, and what we'll do next, a lot of components resistance changes as temperature changes, so it's not necessarily that it's going to be always constant. Okay, that's it.